Well, hello everyone. In this video I will demonstrate techniques for coding in x86 or x64 assembly language in Visual Studio. You might want to ask, why would you want to do that? And in most cases you don't really need to do that, but once in a while you might want to write very highly optimized code, or for instance if you are developing a device driver or write something for the kernel, you obviously might need to use some CPU instructions which are otherwise not available in C or C++, even through intrinsics. Or you might just want to see how it's done and just practice it. So in this tutorial I will show you how to code this for Visual Studio. Obviously it is not going to be a tutorial on assembly language, so I will not be describing all that stuff. And right now let's just see basics, like basic theory, how this can be done. Now I'm kind of recording this for myself as some kind of a guidance, because some of the steps are kind of tricky. So let's try. Now we need to start Visual Studio. I'm using version 2019. We won't really need anything fancy, so let's just create a project. Now I will be using a console app, which is C++ console app, because again I'm not asking for anything fancy, and let's just call it test_asm, and let's just put it on the desktop into the C++ folder. And let's see when the project is created. No, thank you, we don't want to send any feedback. So we obviously don't need C++ stuff here. And let's see, well, we probably need to do some Windows includes for the API. And just to demonstrate, let me start from 64-bit, because it's kind of like, well, easier, I guess. And we will be doing optimized release build. Now obviously I'm doing release because I'll be working in assembly, so I need to see what's going on. I need to remove all the optimization. Okay, so just for kind of like testing purposes, I will write a function and I will put it into assembly language, into its own file, and then from the assembly language I will call another function back into our C code. So just for the test, I will be using some very simple API. Let's just call message box, and this will simply show a message box for the user. So this is the parameters of the call, and let's call it from assembly. Now before we can do anything, we need to create an actual assembly file, and that's just because, again, the Visual Studio doesn't give us a specific template, so we'll have to adjust it. And the thing about assembly and the difficulty of using assembly is that you will have to code it for specific CPU, and not just CPU, but also the bitness. So in this case, we obviously might want to write 64-bit and also 32-bit assembly language. So let's start from 64. And the extension is ASM. So the Visual Studio creates a little bit of a scaffolding here for us, but we don't really need it. So the thing for 64-bit assembly, because it's really simplified, we need a code segment. We need to align it by 16 bytes, and we need to put an end. That's pretty much all we need. Now in this case, let's make sure. Now it has to be included, and it is included, but right now we cannot specify the type of the file, because right now it doesn't participate in the build. So what we need to do, let's see if I can find it. Let's see, I think it's in build dependencies and build customization for the project. Again, you go into your project, right click, and build dependency, build customization, and what you need is a MASM, which is Microsoft Assembler, have to select it and OK it. So now when we go here, we go into properties, we need to change to Microsoft Macro Assembler. Okay, so in this case, when we change the type of our file, it will be actually interpreted as assembly. So right now, if we build it, well, nothing will happen. So we need to create a function. Let's just call it asm function. Now this is the way you create it. And then to end it, you can kind of use the same name, and you put end p, end p. And well, like any function, it needs to return. So this will be our minimum function. And let's see, there's a spectrum mitigation, so we need to, I'm going to disable it. I think it's in C++. It really is not necessary for this test project, so I'm going to disable it. Let's make sure it compiles. It's all the security warnings basically for something that might be using it, but in our case it's just a test project, and it compiled. So just as a example, I guess in this case, let's assume that one of our parameters, let's just go back to our C++ file and let's declare this function. Now it has to be extern C, because it's not a C++, it's a C definition. And just as a test, let's just say that this is a void function. It will be using fast call. Now fast call technically is not necessary for x64, because all the calling conventions will be the same, but we will use it for 32-bit call. Then we need our function, and let's just say that we will be passing a constant string, which will be text. So if we look at our API, let's just pass this text from the C file. And the way this would work, we would just simply call hello world from, we will call our assembly function from the main, and it will pass hello world. So right now, if we build it, as you see, build succeeded, and let's just see what happens. Now if we go into, if we run it and put a breakpoint on the function, I put a little bit of customization for toggle disassembly button here, but you can use Control F11 like it says here to toggle disassembly. So for me, I'm just going to hit this button just to see assembly. So as you can see, our CX will point to our string in memory, and that's according to calling convention. And let's step into, and we're using F11 into our function, and well, it doesn't do anything, it just returns. And then we return, and nothing happens. So technically this is not a very interesting function, as you can imagine, because just returning is not really doing anything. So well, let's write it now. Now according to the calling convention, if you go into Google and just do x64 calling convention, we should probably put Microsoft, but here it is. It will explain how, what, and where. In our case, we will be passing in our RCX register our only parameter. In our case, it will be an address for the string for the message box, right? So we're not passing anything else, and there is no return parameter. Okay, now according to the calling convention for the 64-bit assembly, we need to provide a shadow stack. Now this is just basically 4 memory cells for each keyword, plus the stack has to be aligned on 16 bytes for the next call instruction. So in this case, we have to subtract 40 bytes from the RSP, from the stack, and we have to restore it at the end, like so. Okay, so this will be our shadow stack. Oops, if I can type. And here we are restoring shadow stack. Okay, so then we need to call our API. So if we go back, this is the name. Now we have to use the A version, which is the ANSI, which will allow us to pass a single byte string, and we call it right here. Now then we obviously need to pass parameters. Now just to make it interesting, let's code the type of the message box as a separate function. Let's just assume that the function was located in our C++ file. So now to make it easier for me, I will declare it as a C function, but then I'll show you how to work with the actual C++ function. So it returns uint, and let's call it get message box type. It will be very silly function because it won't really return much. I'll just return the type of the message box. Let's just say yes, no, cancel, and message box icon, I don't know, information. So really, there's no point for this function in real life, but just to show how you can call a C function from actual assembly. Okay, so at this point we need to declare this function in our assembly. And what we're doing, we're using the keyword extern, our function, and this is a procedure, right? So then we can actually call it. Now, as you can see, our function doesn't take anything, but it returns a value in RAX. So since we got it here, we can, well, for now we can wait before we can use it up. But if we go into our calling convention and see which registers we need to pass data in, it's RCX, RDX, R8, and R9. And the way this works, they're kind of going in reverse. So this is RCX, I mean not in reverse, but it goes RCX, RDX, R8, and R9. Okay, so we can start from the last one, and we can say move R9, whatever we got from our function, which it will return in RAX. And let's see, what else do we need? Well, window, we don't have a window, we have to pass a null, and the null we just do ECX, so we null it out. And then we need a title, and the title that we are passing goes into RDX. So let's just add it in the data section, and let's just call it message caption, and we need a 0 at the end, and I'll just say message box text, and need to copy, and let's see, we need address, it goes into RDX, and we got here. And one last thing, we need to somehow move this RCX into R8 register. Now we cannot just do move R8 RCX here, our entry value, because R8 is actually it's a volatile register which can be overwritten here. So we need to technically save it. But how can we do it? Well, we can do push and pop, but the easiest way, we can use the shadow stack, and we can just write it there. RSP, RCX. So again, we're going to save it in shadow stack since we have 5 cells here, and we can just restore it right from it. Okay, so at this point, let's see if it builds. and we have an undefined symbol. In this case, we need to provide another extern. So this is an API. And this is also a procedure. So let's see if that works. Okay, it builds. So let's see if we can actually step into it. Again, we do step into F11. I'm going to change into disassembly. And let's see what happens. So we set up our parameters. Then we call our function. Now our function is really silly. It just returns a constant. So obviously it shouldn't even be here. But just to show it, okay, we got back. And we copy here. We got our R8 back. We got our DX. We nulled out our CX. And let's see if message box actually gets called. And it does. We return. And then we return back to main. And we exit. So as you can see, our little function works really well. Now there is a little bit of optimization here, or performance, I guess, issue. Now let's look at this call, which is, this message box A. Now if I clear all the breakpoints and put it back here, and then if I debug it again, and we go into disassembly view, let's step into it. As you see, we have this jump here, right? So it jumps into this constant. Let me copy it. Let's see if I go copy. I'm sorry, it jumps into this function here, which has this underscore underscore imp underscore in front of it. And then if we step into that after a jump, it actually goes into the actual API and does all the work. Well, the thing is, like, what is this jump? So why are we doing a call into it and then we go into this actual API? Well, if you go into my blog, let me see, if you just go to my website /blog, and if we go into intricacies of Microsoft compiler, it will explain what is this imp and why do we need it. Or if you need a little bit more technical explanation, you can go into the use of imp and imp load prefixes. Basically, just to make long story short, this is Microsoft's way of using import address table. So the imp is actually used internally from C and C++, but in assembly you actually have to use it yourself. So to remove that jump, what we can do, we can actually define our value in import address table and actually use it. So we don't need this. Now the interesting point is that it doesn't have to be defined as a function, but instead it's a variable. It's kind of like a pointer to a keyword or 8-byte address that is stored in IAT, in import address table. And imp is just a global variable. This is the Microsoft's compiler's way of showing where it's located. So if we do it here and if we compile, let's see what happens. So now, if we toggle disassembly, we go straight into the function, right? So when we come out, so we're not doing this senseless jump. So what this basically does, by using this imp, we're kind of like removing that little proxy function that compiler adds for us. Again, in C++, it's not really that important, but in case of assembly, you obviously try to write an optimized code. That will be important, okay? Okay, and lastly, let's see what would happen if I don't do extern C, but instead I would just call a C++ function. Well, if you try to compile it, the compiler will actually give you an error that such symbol is not defined. Well, how come it is defined? Well, the thing is, it's all about symbol mangling. I know it's kind of like Microsoft calls it symbol decoration. So if you go into my blog post, into macro wizardry in Visual Studio and bring it up, I actually provided a little macro here that can actually, I'm sorry, not this one, that can actually help you with name mangling. So let's copy this whole thing over here. I'm sorry, not that thing, but just this thing into our project. And just for the lack of better placement, I'll just put it right here in one file. So what this function does, you can, I guess, read it here in my blog, but basically it shows you a mangled name for this function. Now, before it can work, let me comment this out and comment this out so we can actually compile it. And when we compile, we get this name. Now, this name comes from this little macro that we added, and this name here is the decorated, as Microsoft calls it, or mangled version of this C++ function. So in this case, if we comment it out, go back to assembly. Right now, what we can do, we can actually use this weird looking mangled function from our from our assembly. So now when we put a breakpoint here, and let's go back to toggle disassembly again, I'm doing Control F11, and now if we step in, it's kind of the same thing, really nothing changes from the assembly perspective. But what changed here in our code is that we can call a C++ function. Now, this is not, this is not my favorite way. So what I prefer to actually doing extern C and not worrying with this name mangling. It's just kind of like cleaner for me, but it's up to you. If you want to do it, the other way, that's fine, and that both of them should work. Okay, so now let's do the interesting thing. Now, nobody really codes in one assembly bitness. Quite often, you would have to use also a different bitness. In this case, let's add 32-bit assembly. Now, the problem is that if you try to code both at the same time, the 32-bit assembly is not going to work in the 64-bit configuration and vice versa. So what we need to do, we need to go here, we need to go into properties, and we need to exclude it from build. So when we build 64-bit version, it builds fine, but when we change, that should build. Well, in this case, the 64-bit version should not build. Again, as you can see, I'm adjusting properties and whether or not to build this specific file depending on configuration. You see, it changes every time I switch. This is very helpful. Okay, so now we need to actually code our assembly file. Now, 32-bit assembly is a little bit more clunky, so let's write it. We have to write a little bit of declarations here. This is very old, and you don't really have to think about it. It just defines some basic, important stuff that has to be defined for it to even build. We have to define code section. We have to do alignment by 8. And let's see. Oh, we need an end. And let's see, that should technically build. Oh, and obviously we have to disable that spectre thing. Again, usually you would not be disabling it, but for this, I just don't have it installed on my computer, so it's just not something I need. Okay, and we have a little bit of a problem. Oh, we obviously defined our function here as extern, but we did not declare it in assembly. Well, let's do it. Now, the interesting thing is because we defined our function as a fast call, in x86 it needs special name mangling or special decoration of the name. Now, if you go again to my blog post and go to intricacies of Microsoft compilers, the case of Curious Imp, and search for fast call, let me see where it is exactly. Okay, so over here I'm providing examples of name mangling. So in case of fast call, the function must start with an @ sign, end with an @ sign, and at the end we have to specify the number of bytes that are passed in the parameter. So if we look into our function, which is this one here, it has only one parameter, and we are passing 4 bytes, because again it's a pointer, and in 32-bit it will be 4 bytes. So let's code it, and basically @ sign, name of the function, another @ sign, then we do 4 bytes, and this is proc, and we have end proc, and then we have ret. Now unfortunately, even if you tried to build this thing, it still won't build, because by default when we specify our model as C, the old compiler, the old way, its way of treating the C calling convention or C option or language is to add an underscore, kind of like by default. And in our case, we don't really need this, so we have to disable this. Now, I don't really know a better way as to just use this directive for the MASM. And if I specify it as syscall, it will remove that C model, and then I return it back. So now if we call it, let's see. Oh, we got one more thing. Now for x86, we also have to deal with save structured exception handling. Now in this case, we have to enable it. So if we go into the file properties, I think it's in advanced, and we have to enable it right here. So as you can see, for x64 they simplified all this stuff, but for x86 or 32-bit, we have to do all this. So now if we build it, that should technically build. Okay, and it did. Well, let's see if it works. If we put breakpoint here, debug it, Control F11 to toggle disassembly. Again, ECX 32-bit is used to pass a pointer to a string, and that's because of a fast call convention, calling convention. Let's step in, F11, and well, our function doesn't do anything, just returns, and that is that. Now, to make things a little bit simple, let me just copy and paste here. So again, not RCX, but ECX, oops, will be the address of our string. And just to make it a little bit more interesting, instead of doing return, how about we use a jump to our message box A. Now again, because of the calling convention, you have to see, well, you know, the easiest way is if you go here and go into C++ file and just do message box, then right click on it and peak definition. We can tell this is Win API. Well, Win API doesn't tell us much because it's a macro. We have to do another one, peak definition. And we can see that this is std call, right? If we go back to my blog here, std call expects an underscore, and @ and then at the end is the number of bytes that are passed into parameters. So if we look, let's remove this, or just actually look right here using IntelliSense, we have 4 parameters that we are passing in. So let's see how the name mangling would work. Now unfortunately, you have to do all this stuff manually in assembly language, because again, that's just what assembly language is. So if we go into extern, we have to define it. Now, because we are in the C calling convention, in the calling model, the assembly, the compiler will add underscore for us, so we don't have to worry about it. What we need to do is to add @ symbol, and we need, you know, number of bytes. Again, if we look at the function, it has 4 parameters, each requiring 4 bytes, so we have 16. and this is a proc. Okay, so at this point we can call this whole thing from our jump. Well, let's see if it works. Now it compiles. Problem is, obviously we can't call it like this because we didn't specify parameters. Now before we can do anything, we need to call our test function here to get the actual type of the message box. And before we can do that, we have to specify it as extern procedure. Okay, well, we have this ECX that is passed. Now unfortunately, when we call this function, ECX is a volatile register which can be overwritten, even though it is not, but we cannot rely on it. So we need to save it. Let's just push it into stack. That's the easiest way, and then pop it off the stack. Okay. Now for the calling convention we're using here, we have to pass all the parameters for message box on the stack. So the window handle, as you can see here, is 0. So kind of like go back. Then we push our ECX, which is our parameter. Now over here, let's just skip one line. We push EAX, which is, the type, which is the last parameter. Okay, then we need to get an address for our string and then push it. Again, I'm just using EAX, just kind of like override it. And okay, and that's pretty much it. Let's create our string. It goes into data segment. And we can pretty much copy and paste it. It's kind of the same thing. And we add it here. Okay, so let's look at it. So we create a H window, which is null. Then we create text. Now the text comes from ECX. And ECX is what comes from the outside. You see, we push, we pop, kind of like saved it here, and then we add it as a parameter. Now then this one is a caption, and the caption comes from here, which we specify as a data. And let's see, and here we use the last parameter, we use the type. And EAX comes from our function, which is called here. So this is our type. Now, if you run this thing, it would still create a problem because we're using a jump here instead of using a call. Now, a call would surmise that we would provide a return address. So right now we don't have it. So the easiest way is to get it. Now, the way we can get it is if we pop, let's say in one of the registers here, it from the stack, and this is our return address. And as you can see, like here we push something, we called, then we returned, and then we pop something. So ESP, or the stack pointer, will be the same as if it was when we just got into this function. So in this case, EDX will contain our return address. So all we need to do is to push it back. Yeah, let me just say that this is return address before we actually do our call. Now let's see if this works. Okay, it compiled. Let's debug. Let's step in, toggle disassembly, and let's walk through it. So we get here into our function. It just returns our type in EAX. And then we come out, we get our RCX, which is our pointer. We pop EDX, we pop return address into EDX. It's, let's see, where is it? It's this one. We got EAX, which is our caption. And then we call message box. Again, we jumped into our unnecessary jump here. We'll deal with it later. And then we go into the actual API. displays our message box, and then when we come out, the function ends. So let's just run it to make sure it works, and it does. So how can we get rid of that unnecessary jump? Well, the thing is exactly the same. So instead of using this, we can use, well, again, if we go back into my blog post, we can use the imp prefix, this thing here, and we can just put it in front of our function. The thing that you have to remember in here, because we have a C calling model, we have to remove one of the spaces here, one of the underscores. Obviously, we have to also do the same here. Okay, so now when we run, it gives us an error. Well, the reason we do this, well, first of all, we need to define this as dword. This is so easy to do. And another mistake that I made, I need 2 underscores, because again, the C model adds it automatically. So okay, add it here, and we need to add it here, and just for readability, let's put it into brackets to say that this is read from this global variable. So let's see if it builds now. Okay, so let's step into it and toggle disassembly. And then if we get to our actual call, as you can see, we are getting into the actual API that makes our function work. So again, by using this imp prefix in front of the function, we kind of get rid of that unnecessary jump, which, you know, a compiler adds for us, actually linker. Okay, so this is basically how you build, you know, assembly. Now this is again not a tutorial for assembly. I kind of went really quick through it. Let's make sure that both 64 and 32-bit versions build. So, and they do, and let's make sure that they run. So this is 64-bit, and this is 32-bit. So as you can see, they both do the same thing, but because we were coding it in assembly, we had to do a little bit more work here. Obviously, you have to understand calling conventions and, you know, all the shadow stack and such, but this is how you can add both 64 and 32-bit bitness code, assembly code, into your C++ project. Okay, well, thank you for watching, and I will see you guys next time.